Okay, good morning. So we continue our lesson about set theory. So we learned about sets. Uh, for example, we learned that we learned first of all that we are not supposed to define sets because whatever we do to define sets does not work. For example, I can say that a set is a collection of objects. Then you might ask what a collection is. So this will go forever. Okay. So it's a primitive notion. A set is a primitive notion, a primitive notion in the set theory, but we learn how to describe it. So a set is a collection of objects, more or less, that any object in the world is either inside it or not. Okay, even if we don't know at the moment which one is true, but there are only two possibilities for any object regarding a set: either that object belongs to the set or not. Yes. And then I told you that so there are some rules that you are supposed to respect them. For example, if I want to denote a set, usually it is common to denote them by capital English letters. And then you, for example, put equality sign, and then you have to use curly brackets. This is a have to. And then you list the elements of the set inside that and separate them by a comma. For example, I can say 2, and then comma, I can write pi, and then I can put a Greek letter there, and then I can put an object there. Well, it doesn't matter what you put actually inside. So this is a set consisting of these objects as its elements, yes? So you can say that 2 belongs to the set A, or I don't know, this star or whatever it is, it belongs to the set A. But for example, a square root of 3 does not belong to the set A. So each one of these that you see inside is called an element or a member. Or a member. And now let me also talk about this. There are two category of sets. We can categorize sets in different ways. One way is depending on the number of elements it contains. So here we have a finite set. So we can have a finite set, or we can have an infinite set, yes? I think you already have an idea what is going on. If you can count the number of elements of a set and assign a natural number to it, then the set is a finite set. If not, your set is an infinite set. For example, the set that you see here right now on the board is clearly a finite set. Because if I ask you how many elements are there, you can really start counting them. Yes, you can say 1, 2, 3, 4, and 5. So there are 5 elements in this set. So that's a finite set. But on the contrary, if I write the set of natural numbers, so usually this is a little bit deviation. Usually we do not write it with n, because these are so ubiquitous in mathematics, we want to assign a new character to them. So this is why when you see this n equate with a little bit of line next to this definitely means the set of natural numbers. Okay, so these are the symbols we use, okay? So the set of natural numbers, if we start from 1, the first one is 1, the second one is 2, the third one is 3, 4, but you know that this list will continue forever. So this is a very simple example of an infinite set. Well, this is an infinite set. Another notion that we had it before, it's called cardinality. So what is a cardinality of a set? It's just a fancy name given to the number of elements of that set, yes? So when I say cardinality of A, I mean how many elements are there in your set A. So cardinality of A here is 1, 2, 3, 4, and 5. And the symbol that you use for it is this. You write something very similar to the absolute value sign. So you write this equals to 5. So this means the cardinality of A is equal to 5. It means the number of elements in A is 5. Of course, here, it's not a good way of writing, but sometimes people write the cardinality of N is infinity. Yeah, usually we don't use it, okay? I don't like it that much because infinity is not a number, so you cannot treat infinity as you treat numbers. Okay, so I would say that don't write it. But I want you to know that the cardinality of this set is infinite. Okay, another infinite set is probably, is the set of integers. And exactly this is the reason that I put this line again here, yes? So if you want to generate this, for example, in a typesetting system, math, LaTeX, you just write this MAT and then BB, and then, for example, you put Z in curly brackets. Then it will generate you exactly this symbol. Okay, so what is Z? Z is actually, it's minus some dots here, -2, -1, 0, 1, 2, 3, and etc. So what is the cardinality of Z? In this sloppy language, again, infinity. So it means that this set is also an infinite set. By the way, this concept was also puzzling mathematicians in the beginning of at the end of the 19th century, that the number of elements here, we say it is infinity, and the number of elements here, we say it's infinity. But can we compare these two infinities? For example, at the end of the day, if someone asks you, is the number of elements, how you compare the number of elements here and there? Of course, you can say infinity for this one and infinity for this one. You might intuitively think that, okay, so this one is bigger than that one. Okay, but that's a wrong conclusion. So then these infinities are of the same order. So you have to believe in that. If you want, we can discuss a little bit about this as well. So the number of elements here and the number of elements there are apparently the same sizes. How we can see that? This is a little bit subtle to understand, but we can understand this one. For example, let me write the set of natural numbers. And this list continues. And then I would write the set of even natural numbers. Yes? So let me just denote this by N, and let me denote this by E. Yes?
Hold on.
Yes?
Why did you write 8?
Oh, that's my mistakes. And I made 2 mistakes. Yes? 5, and this is 10. Thank you. Okay, which one of these sets do you think contains more elements? Once we have the set of all natural numbers, and then we have another set which is just the even natural numbers. Yeah.
The natural numbers?
Yeah, but it seems that the natural numbers intuitively should contain more elements. But I want you to understand, no, they have exactly the same number of elements. Of course, the same number of elements is a little bit ambiguous, because if I ask you how many elements you see there, you should tell me infinity. And if I see how many elements you see here in the second list, you say infinity. But intuitively, you believe that that infinity should be somehow double in size of this infinity. But this is not true, but you need to understand it through pure logic. And I want to, this is not very hard, by the way, to understand, even though this is an optional discussion. It is not included in your book, but it is not something that you really have hard time to understand. Intuitively, it seems a little bit counterintuitive, but let us try to understand it in this way. Okay, so for example, if I give you a box with some elements here, let me write it a little bit in order. And then I give you another box with some other shapes. Let me try to give them letters here. And then let me just give you some shapes here. Okay. So if I ask you how many are the elements in these two sets the same, of course you would immediately answer yes. How do you answer that? Usually, how do you answer what? Why the elements are the same, the number of elements are the same? Yes? You just count them. 1, 2, 3, 4. 1, 2, 3, 4, so they are the same. But the point of counting is not possible in this case, because you will never ever finish counting. They are infinite. But assume that I want to justify that the number of elements of these two sets are the same without counting. Can you find a way to do that? Assume that, by the way, this is, I think ancient shepherds, they didn't know how to count, but they can take take the number of elements, the number of sheep that they have, actually. Okay, yes?
If you just draw lines between them.
Yeah, exactly. And that is called one-to-one correspondence. So, for example, you say that I take one of them, and I connect it with one of these objects from the other set in my head. I take another one, connect it with another object. I take this one and connect it with another object. I take this one and connect it with another object. I didn't count, yes? I just try to make a one-to-one correspondence between the elements of these two groups. And what happens at the end? If for every one of these elements there is exactly one element there, so the conclusion is that the number of elements of these two sets should be the same. Because if there are more elements here, and then there are only 4 elements and 5 elements here, this is not possible to give a line to this last one. If you want to do this, you have to take one of these again and connect it to this one. And the notion of one-to-one means for each one, you want to have only one. I mean, this idea of one-to-one correspondence is something we can understand in this new picture. So for the case that we have finitely many elements, of course, it is not hard to count the left-hand side, count the right-hand side, and compare the final numbers. But if I don't want to count, this is also one way it works. Yeah, is that clear or not? Yes. So that this idea is the same. I want to tell you that this idea actually works here, because you connect 1 to 2. Yes. You connect 2 to 4. You connect 3 to 6. You connect 4 to 8. You connect 5 to 10. Do you think this process will ever stop? You can feel that you can continue this. Yes. So it means that if I have 100 here, this 100 is connected to exactly one number in this list. What that number is? If I reach here to 100, what do you see here?
200.
200, yes? And if you see 1000 in the lower row, what is that number above, which is connected to 1000? 500. If you want to understand it, you can imagine like this. You can imagine that we have a classroom with infinitely many seats in it, numbered 1, 2, 3, 4, 5, etc. And there are infinitely many students outside the classroom. They are supposed to come in, but because there are infinitely many people, I want to organize them that I will prevent a mess going on. So what I would say like this. I start giving labels to them. I call one of them and give the first one label 2. Okay, and then I call the second one. So for example, they are coming in a row in, and I give the label 2 to the next, label 4 to the next one, label 6 to the next one, label 8 to the next one, etc., etc. And I give them, because there are infinitely many seats and it might be a mess around, so follow this rule. Divide the number that you have, and then find the seat in the room and sit down on that one. Okay, the person who has label 2 divides the number by 2, it becomes 1, and will go into the room and take the seat number 1. And then the person number 4 will go and sit number 2. Yes, the person number 6 will find a room and find a seat and go and sit on row number 3. And I hope that you agree there will be no seats empty. There will be no seats occupied with more than one person. On the other hand, there will be no person without any seats. Yes, everyone will find a seat. So what is the conclusion then? The conclusion is that the number of these two sets should be the same. Yes?
Do you mean there's no person 3?
No, there's no person 3. I assign a rule to them, okay? But I just want you to understand that every person with an even number, according to this rule that I established, will find exactly one seat. Okay? No chair will be left empty at the end. Yes?
So what happens? So like, if we're to continue this example, what happens if like after this, another infinitely large group of students comes and finds out, oh, we're supposed to have a lesson in this classroom. So how would you do with if another infinitely large group of students comes?
No, in that case, I have to establish the rule, another rule.
Yeah.
Yes, that's actually that is the. I just want you to understand that because we can go with this very far away from our lesson, but I just want you to understand. I hope that you understand the first intuition that the number of elements in the first list should be double in size is not that correct logically. Yes.
I'm just saying because I've heard this I remember because I heard this very similar example, but instead of with a classroom, it was with a hotel.
Yeah, I know that. I know that example, but there is also a good video. I can find it and share it with you.
I think
By
we
the
talked
point.
about it in some math lesson, like in math 1 or 2.
Oh, I don't know what, but yeah, it might be. But because this is also understandable in math 1, see, this is not a very hard topic, yes? So I just want you to feel the number of elements in this set. According to this logic and what I described here, you have to accept at the end the number of these two elements. Of course, we cannot assign one single number to the number of elements. We say the number of elements here is infinity, the number of elements here is infinity. The first intuition is that this infinity somehow should be double in size with respect to the other infinity, but I just want you to understand that this is not the case according to this reasoning. But I just want you to see, do you understand what is going on, what I described? Okay, but this doesn't mean, and then of course the rule here is more complicated. So the rule that I established here, I gave students labels 2, 4, 6, and 8, and I told them what to do to find your seat, but just by dividing it by 2. This rule, of course, will not work here. That's also a good exercise for yourself if you can establish a rule that do the job for me here. Assume that these are the number of seats here, but you have students labeled with these numbers, and then you want to set up a rule that everyone will go inside and find exactly one seat to sit on. Of course, I hope that you agree that this rule is harder than that rule, but this is also possible. Okay? And then it's interesting that if you go to the rational numbers, that is also the same. So these orders of infinities are all the same. But suddenly, the number of infinities in the real numbers is much bigger. So if you go to the real numbers, the number of elements here is also infinite. So this set is also an infinite set. But the number of elements there is actually much larger than the number of elements of each one of these two sets. So I mean, this infinity is on a higher order than these two infinities. Okay, so that is something that it is good to know about the infinite sets. Any questions here? Okay, So we also talked a little bit about this empty set. Do you remember? So the empty set is the set containing no elements at all. We have two symbols for this. Is the symbol that we use to denote the empty set. But if I ask you to write it down, you can write it like this. Okay, another thing that I haven't talked about that yet, I want to talk here. Most of the times, not most of the time, sometimes we write these elements of the set, but sometimes we describe them. For example, I can say as a set B, the set B is the set consisting of x's where I can say x's belonging, for example, to n. And then I would say such that, this is the way that you read it. So this is the set consisting of x's, which belongs to the set n, but such that, for example, we have x squared minus 5x plus 6 equals to 0. So this is a description of the elements of the set. So you see, I haven't listed the elements explicitly. I have given you a rule to read the rule and understand about the elements of that set. So how do you read it? You say that the set B is equal to the set consisting of x's coming from the set n. This is such that in your book, instead of this, they have put semicolons. Both of them are acceptable. So this means such that x squared minus 5x plus 6 is equal to 0. For example, I can give you this set, and I can ask you what is the cardinality of this set. Okay, so for finding the cardinality, you need to know the number of elements that are in this set. So what is your suggestion for me? How should I answer this question? Yes?
You can solve for x.
Yes. So I want to find all possible natural numbers that satisfy this equation. So this means that I have to go and solve that equation. Okay. And then what do I get? For example, let us use factorization. Okay. And then I will get x is 2 or x is equal to 3. Okay, so what is B then? If I want to write all the elements explicitly, this set can be represented by 2, 3 or 3, 2, because you remember the order doesn't matter. And then, of course, if I ask you what is the cardinality, you can immediately answer that the cardinality is 2 because there are 2 elements in my set. So, for example, what do you think this set is? C is x in R such that x squared plus 1 is equal to 0. What this set is? How do you read it? The set C is equal to the set of all x's in the set of real numbers, but with extra property that x squared plus 1 is equal to 0. Yes?
Would be 0 empty.
No, 0 or empty.
Oh, the empty set?
The empty set. You cannot say it is 0, yes? Because I'm asking you what this set is. So you open the curly brackets and try to find all possible real numbers that satisfy this equation, but you know that there is no real number satisfying this equation because x squared is always non-negative, and when I add 1 to it, it cannot be equal to 0. So there are no sets, there are no elements here. So you open the curly brackets to write the elements in, but there are no elements, so then you close it. So what is the card? So this means that this set is actually the empty set. Yes? So what about this set? So let me call this D. How do you read it? The set of all real numbers, the set consisting of all x in the set of real numbers such that x is not equal to x. Yes?
Yes, empty set.
That's also empty. Because whatever you choose from real numbers, it is equal to itself. Yes? This tells you go and find a real number which is not equal to itself. Can you find such a number? No. So this means that it's also empty. So can I say that the set C is equal to set D? Yes, because both of them are equal to the empty set. What is the cardinality of D? 0. Yes. So we can write a set like this. So what is the cardinality of this set? Or what are the elements of this set? Let us write it explicitly. So this tells me that go and find x's where coming from n so that x squared plus 5x minus 6 is equal to 0. So one good way is to solve that equation. And then of course you know how to solve it. Let us just factorization is easier here. So I need two numbers whose sum is positive 5 and the product is minus 6. So what are those numbers? No, 3, 2 doesn't work, yes? So it is positive 6 and negative 1. Because if I add them, it becomes positive 5. If I multiply them, it becomes minus 6. And then the product of two numbers is 0. I have two possible answers. It's minus 6 or 1. Okay, so what should I write here? I open the curly brackets. I need to find possible numbers from the set of natural numbers satisfying this equation. And then after I am done, I close the curly brackets. So what numbers I should write inside? Yes? Only one. Because even though minus 6 satisfies this part, that does not satisfy that part. So this becomes only 1. So this means the cardinality of E, for example, if they have asked that one, is just 1. So in order to have an element inside your set, you should satisfy all the conditions that you write here. For example, I can write something like this. Let me add something to it. D, I would say that x belongs to n such that x squared plus 5x minus 6 is equal to 0. And let me write and x is between minus 3 and strictly less than 0. So what that said is, every calculation you need is still on the board. So what is this D? This D tells me that I am interested in all natural numbers such that they satisfy two conditions, this one and that one. Okay? So what is that? What's the answer to this?
The empty set.
This is the empty set again. Yes? Because the only numbers that satisfy this are these two, but none of them will satisfy the other condition. So this means that is empty. So what do you think will happen if I write or there? Do you think it will change? This means or. So what is the answer to this one? That's again 1. Yes? Okay, let me now write the same thing, but let me change this from N to R. Okay? With N, the answer was 1. But I changed n to r, and I cleaned this weight for you again. So what is the answer here? Yes?
For the first part, it's only 2 options, but for the second part, it's many.
Okay, but what is the answer at the end? Yes?
Yeah, I think it's infinitely large, right? Infinitely many numbers.
Okay, that is a different story. But what is that set? These are important things I want you to learn. When I say what the set is, you cannot tell me there are infinitely many of them there. I'm asking you about the set. Okay, you should be able to describe them. Might be we do not have enough knowledge right now, but you cannot say that. Of course, you are right. This statement is true. There are infinitely many. But what are they? Yes.
It means like describe what's in the brackets.
Yes.
Okay, so say that when it's a set of all real numbers that satisfy either the equation x squared plus 5x minus 6 or the difference -3 is less than or equal. No, yes, it's less than or equal to x, which is less than.
Yeah. So let me write it. If I just write this, do you agree with me or not? And if not, why? I would say that this is equal to just write this. Do you agree with me? Yes, Aaron?
No, because you didn't include -6.
Yeah, I have also to include -6. And that is something we will learn today, hopefully. That is called union. So I have to write union with one single element -6. That's why I told you that we haven't studied that yet. But at least I want you to understand, if I change and to or, it have some consequences might be, and that is the consequence. Okay, I will not discuss about this now. I just want you to understand that there are differences here. So you have to have a good interpretation of how you want to write it down. Okay, so that is also something, this is the new lesson, how to describe a set in a mathematical language rather than writing all the lists. Yes?
I also want
Also?
1.
Yeah, also 1. Okay, thank you very much. Yeah, 1 is not already included here. Yes, also 1, thank you. Thank you very much. Okay, so this is something, that was a new lesson, but let me also go back a little bit what we had before. Do you remember the notion of a subset? So I have two sets A, another set B. First of all, let me ask you, when do we say that these two sets are equal? Yes?
When all the elements are equal. So all the individual elements are equal to another element on the.
This is not a good. This is not a good statement in the set theory language. So when do you say two sets are equal?
They have the same amount of the same elements.
So meaning every element of A is an element of B, and every element of B is also an element of A. It's extremely important to express it without ambiguity. Okay, and then when we say A is a subset of B with this symbol, do you remember what do we mean? Yes?
Not really that, but I have a question. Does the order matter in mathematics? The order of numbers, like?
No, in mathematics sometimes it matters, sometimes it doesn't, but in sets, no, it doesn't. I want you to define this symbol. When you see this symbol in mathematics between two sets, what is the message here? Yes?
That all elements of A are in B.
Yes. So it means that for all x, if x belongs to A, you can see that also x belongs to B. It implies that x belongs to B. These kinds, you don't see them in the book, but they are not hard to understand. This upside down means for all. And then, of course, this means implies. For all x, if x belongs to A, then x belongs to B. That's the definition of A subset of B. Okay. Do you remember we had some rules for this? For example, I just want to ask you, do you remember what was the rules, the important rules about this relation? For example, can I say that every set is a subset of itself? Yes? Yes. Every set, whatever it is definitely a subset of itself. I hope that you understand that. Why? Because according to the definition, this symbol is true. This relation is true if whatever is in A is also in B. But A means the left-hand side, B means the right-hand side. So is this true or false? I have to check this. Everything on the left-hand side, is it okay that this is also on the right-hand side? Left-hand side is also in the right-hand side? Yes, whatever I choose from the set on the left, it is automatically in the set on the right because these two sets are the same. So remember this fact that every set is also a subset of itself. Of course, every set is equal to itself, but it is also a subset of itself. Okay, do you remember the relation between empty set and A, which was a little bit counterintuitive? So if you give me any set, and even if I don't know what are the elements of this set, can I write this for sure or not? So that was also true, remember? So empty set is a subset of every set. Because if you say no, what does it mean? It means that you were able to find something here which is not there. But this is not possible. Okay? So we say this is vacuously true. So rule number one, every set is a subset of itself. The empty set is a subset of every set. But do you remember what was the notion of the universal set? Yes?
Every set is a subset of the universal set.
No, before that, this is the universal set. It means that whatever set you are working, the elements are coming from here. And because of the definition, as you said, you are right. Every set is also a subset of the universal set. So this is the universal set. Yes? And then we had one more rule, if you remember. What was that? If a set A is a subset of another set B, and then if the set B itself is a subset of another set C, what can I conclude from here? What can I conclude? I can conclude that A is a subset of C. This is called transitivity. And we had something called Venn diagram. Do you remember? Let us just remind you about that because that's a long time ago, more or less. So what was the notion of a Venn diagram? Because our brain, I think, has evolved to understand graphics better than abstract things. It's better to be able to draw some graphs to understand things better. In that picture, so the Venn diagram, yes? So in this picture, the universal set is represented by a little bit bigger rectangle. And every set is supposed to be something like a circle inside. You don't have to obey that this has to be a circle. It can be anything. So, for example, this is set A. I can have this to be set B. I don't know. I can have this to be set C or whatever. So this is called a Venn diagram. If I want to draw a Venn diagram to represent a subset relation, for example, what is a good way to draw that? For example, this is the universal set. I would say that this is B, this is A. I draw A completely inside B. This represents that A is a subset of B. So if you want to represent A is a subset of B using some kind of graphic things, then you can just draw it like this. So this means that whatever you see inside A, of course, it is already inside B as well. Okay, let me just try to have some analogy between this relation among the sets and this relation among numbers. Because sometimes people compare these two. Of course, these are different things, yes? If you see this symbol, you expect to have a set on the left and a set on the right. If you see this symbol, you expect to have a number on the left and a number on the right. For example, this is meaningless to write. Yes, this is meaningless. Because this is a set, that is a set. I cannot compare these two sets with this symbol. So this is meaningless. This is also meaningless to say 1 is a subset of 2. This later, in more advanced mathematics, becomes sensible, but for the time being, it is meaningless. Yes? I want you to understand this, whenever you see this, you expect to have two sets on the sides. Whenever you see this, you expect to have numbers on the sides. But, yes?
You forgot an S.
Meaningless, yes. Okay, so now my question is that, okay, of course this is, I don't want you to talk about this, but let us talk a little bit more. First of all, can you, for example, can you tell me an analogy, a similarity between this and that? Of course, this is in the realm of sets, this is in the realm of numbers, but can you see some similarity, a property that this enjoys, the same property, this somehow similar property this one enjoys? It is on the board. Yes? Yeah?
I'm thinking of the rule like A is less than B and B is less than C.
Yeah,
and C is less
that is one similarity. Because you know that if A is less than or equal to B, if A and B are numbers, and simultaneously B itself is less than or equal to C, of course, you know that you can conclude that A is less than or equal to C. So that is correct. So that is also called transitivity. So both of these relations enjoy transitivity. Do you see another similarity? So this rule somehow was correct when it comes to this relation. Any other one on the list? Yes?
Could we maybe say something like with the universal set, so any number is less than infinity, something like that?
Yes, but I don't see this here.
Well, you see A is a subset of the universal set. Could we technically say
Yeah,
that
I haven't thought about that, but now when I'm thinking this might be good. Yes, you can say that every number is less than or equal to infinity, yeah, something like this. Okay, one more. The first one, yes, every set is a subset of itself. We have also here, any number A is less than or equal to itself. This is called reflexive property, both in that case and in that case. So that is reflexive. Okay. What is the big difference between these two relations? Or what is the difference? Of course, because when I say what are the differences, you can start giving me a long list of differences, yes? But what is the main difference? Yes?
Well, the subset thing concerns sets and.
That's what I'm saying. Forget about these things. I mean, what is the big difference between them? The big difference is that when you use this symbol, every two numbers are comparable according to that relation. What does it mean? It means that if you just give me two random numbers, for example, A and B, either this one is true or that one is true. If you give me just two numbers, two random numbers, A and B, either this one is true or that one is true. This is definitely the case. For example, if you give me two equal numbers, in that case, of course, both of them are true. But if you give me 1 and 2, 1 is less than or equal to 2 is true. But that is not the case when it comes to this symbol. It means that you can give me two sets for which none of these are true. Yes? Can you give me two sets for which this is false, this is also false? You cannot give me two numbers so that this is false, this is also false. Do you agree with me? There are no possible choices for A and B for which this and that are simultaneously false. But for the case of sets, this is quite common. Yes, you can give me a lot of sets, not only two sets, for which both of them are wrong. For example, I want to hear from you. For example, what?
1, 2, 3, 4, 5, 6.
Yeah, make it as okay. 1, 2.
1, 2, 3, and then the other 4, 5, 6.
Okay. The other one.
Yes.
Okay, yes, that's good. 4, 5, 6. Yes. Is A subset of B true? No, it's false. The other one, B is a subset of A, is also false. So this is why you cannot order the sets using this symbol. It's not a total order, it's a partial order. Yes? It's not a total ordering. I'm just spitting out these words, but I want you to get familiar with them. But I want you to see that if I give you a bunch of numbers, you can arrange them in ascending order, for example. I can ask them to write them from the smallest one to the bigger one, and then you can do that. But I cannot give you a number of sets and I ask you to arrange them using this as an order. Because it might happen that there are two sets in your list for which none of these are true. And then you don't know, should you write A first in your list or B first in your list? You cannot order them. So this is somehow an order. It's a partial order. It's not a total order. Yes, Hossein, you have questions?
Can you give another example?
Another example of what? No, you have to be explicit. Another example of this one?
Yes.
Okay, there are many examples you can construct. For example, A is equal to 1 and 2. B is 2 and 3.
I mean, with big variables.
Pardon?
Is it possible with variables?
May you speak louder?
With variables.
Oh, it doesn't matter. You can write X and Y and Z, for example. Yes?
Except in that case, there is a subset because 2 is involved.
No, there is no. Be careful. So there is something you are missing. I am saying that is A subset of B true or false? Here in this case, A is a subset of B is false. It's not something gray. It's black or white, yes? A is subset of B is false. Why? Of course, they share something they have something in common, but is it true that every element of A is also an element of B? No, because I can find at least one element, one, which is in A, but not in B. So this is false. What about this one? For these two sets. False or true? False. So, can you say which one is bigger? Here, you can immediately, if I give you two numbers, you can say which one is bigger, okay? But here you cannot say which one is bigger because none of them is actually like that. Yes?
If you have like some elements that they share, is there a sign for that?
Yes, we will reach to that. But for the time being, I just want you to understand both of them are false. Okay, so now let me ask you, do you think this relation, this is also a relation, because if I give you two sets, you can say if this is false or true. For example, let me just play around a little bit with this, and I want you to compare these two symbols. They are really not the same at all. They have something in common. They have some relation between, there is some relation between them, but you have to respect the differences. For example, if I write A to be A, can I say that A belongs to A? Yes or no? That is clear. A belongs to A. But can I say A is a subset of A? So be careful. So this is true. But this one is even meaningless. Because when you see this symbol, what you expect is to have sets on the left-hand side and the right-hand side. So the right-hand side is a set, but the left-hand side is just one single element. Yes? So we cannot even use this symbol. But, for example, let me write this one. How do you understand this? This means that this is a set. What is the cardinality of this set here? 1. Do you understand what is the meaning of this? This is a set, contains how many elements? 1. But what is the name of that one element? Is curly brackets A itself. So this is a set whose element is another set. That's possible. Yes. So this is a set whose element is another set. What is the cardinality of this set? Is still 1. But is this true or false?
No, false.
This is false. Because if I ask you what is the element of A, the whole package you see here is the only element of A. And when I write A belongs to A, it is not true. Yes, it is false. Okay, what about this one?
True.
At least this is not meaningless, because whenever you see this symbol, you expect to see a set on the left, which is true, it's a set, and you expect to see a set on the right, which is also true, because A is a set. So it is not meaningless, okay? But then it might be true or it might be false. So how should I see it is true or false? Is it true or false? True or false? So true, raise your hands. Okay, false, raise your hands. Okay, and the rest of you are neutral. Yeah, it is false. Yes, because when you say this is true, what does it mean? It means that every element of the left-hand side should also be an element of the right-hand side. This is the meaning of this symbol. But every element of the left-hand side, what is the only element of the left-hand side? Is A. Does A belongs to A? You just say this is false. So if this is false, this also has to be false. That's also false. Is that clear? Okay, so do not mix these symbols. So for example, what about this? Let us make it a little bit interesting. So I would write here A, and I will write here curly A, curly brackets A. Let me ask you, what is the cardinality of this set now? 2. One element is this, one element is this package. Okay, now let me ask you, do you think this is true or false? True. Because of which one? Because of that one. Yes, because A is an element of A. So that is true. Okay, what about this one? This is also true. Yes, because whatever you see, what is an element here? So if you want to see if this is true or false, you need to check this. Everything in this should be also here. What is everything here? Just one thing, and that is A. Is it true that A belongs to A as well? Yes. So that's also true. Yes? Is that clear or not? So these two statements are simultaneously true in this case. By the way, when you are good in coding, I think you should be very good in these things. Yes, might be, I don't know, in Python or whatever you are using, you are working with lists a lot, yes? And then you have lists of lists and lists of lists of lists, and that's the same story, yes? Yes, but you need to understand them in a set theory language. Yes, please.
Yeah, so I'd just like to clarify the previous one with the two falses. So theoretically, for the first one, A belongs to the set of A.
This one, you mean?
No, the row that
Yeah.
in the middle, the one in
Yeah.
the middle. Yes. So
Yeah.
if you were to put curly brackets around A, then it would be true, right?
Yes, let me write that one as well. Thank you.
And also want to talk about the one to the right.
This is a good question.
So for the one, for curly brackets, A is a subset of A. If you were to put another set of curly brackets, then it would be true, right?
Yes, for this one.
Yes.
These are good questions. Yes. Why that, by the way? Because this, whatever you see on the left is the set A itself, and you know that every set is a subset of itself. These are, I don't know why I forgot to write them. Thank you for asking. So false, false, true, and true. Yeah. Yes?
What happens if the first A also gets curly brackets in the third row?
No, this is not good, because if I want here or here.
Yes.
Okay, here it doesn't make sense that much, because why do you see, you shouldn't see this in principle. Why is that? You never see this in the set theory context. Why? It is not forbidden, but you don't see it usually. Why? Yeah. Yeah, because I told you that repetition of the same element doesn't change the set. So it is common that when you write a set, you just don't write repetitions. You don't write things. So this set for me is just this set. So you are not allowed to repeat elements of a set. Because if you do, you are not generating a new set, you are generating the same set.
Aren't you changing the cardinality though by adding?
No, that's what I'm saying. If I ask you what is the cardinality of this one, you should say 1.
It's 1.
1.
So it only refers to the amount of unique elements.
Yes, yes.
Okay.
Yes?
Another curly brackets, 2 of them.
I will. Just be patient a little bit. Okay, so now I'm asking you a question. Can you give me, for example, 2 sets, A and B, so that this is true, this is false? We have it on board, but let us repeat. I want you to give me 2 sets for which A belongs to B is true, this is false. And then I want you to give me an example for which this is true, this is false, this is true. And I want to give me an example for which both of them are true. But of course, both of them are false. I don't think it's a big deal, but we can write all of them. So I want you to give me 2 examples of set A and B for which, let us have 4 examples here. 4. Okay, so do you have anyone for this one? A is what and B is what? Yes?
So you could have A be, I don't know, like 1 and 2.
1 and 2?
Yes, and the important thing is B. The B contains, the set of 1 and 2, so curly brackets 1 and 2. So then you could say that A belongs to B.
Yes.
And but I think
you're right. This example is exactly what I want.
Okay.
Yes. I want you to understand. If you have any questions, please let me know. So A is curly brackets 1 and 2. What is the cardinality of A? 2. What is the cardinality of B? 1. This is the only element in B. Okay, so A, which is this one, is an element of B, yes? If I ask you what is this is just A. So A belongs to B, that is true. But A is not a subset of B. Because if A is supposed to be a subset of B, what does it mean? It means every element of A should be an element of B. But is that true? No, because, for example, 1 is an element of A, but is 1 an element of B? No. So this is why A is not a subset of B. So the first one is true, the second one is false. Okay, give me an example for which the first one is false, the second one is true. That's simple, yes? Give me an example. Yeah, make the example as simple as possible, okay? Yes?
A is 1, B is 1 and 2.
You mean curly brackets 1 and then curly brackets 1 and? Yeah, that's the standard example. So, do you agree that A belongs to B is false? Yes? Because what is A? A is the whole package. Curly brackets 1. But curly brackets 1 is not among the elements of B. So A belongs to B is false. But A is a subset of B is true. Because whatever is an element of A is also an element of B. Is that clear? Okay, now give me an example for which both are true. That is more interesting, the most interesting part probably. Yes?
We could take the first example, but add 1 and 2 to D.
What?
Would that work?
What should?
Yeah, so 1 and 2, that's 1 and 2.
1 and 2.
And B is both the set of 1 and 2 and 1 and 2.
Yes, 1 and 2. 1 and 2. Yes, this is what you mean. Yes, let us check. A belongs to B. Everyone agrees that this is true because A is this one. And then you see this exactly as one element in B. So definitely A belongs to B is true. But what about A is a subset of B? Let us check. When I want to check this, I have to check every element of A is an element of B. Elements of A are 2 of them. There are 2 of them, 1 and 2. Is 1, which is an element of A, also an element of B? The answer is yes. Not because of this one, because of that. Is the second element of A, which is 2, also an element of B? Yes, because of that too. So you are right. For these 2 sets, both of them are true. And of course, the last one, you can just write 2 non-relevant sets. Yes, for example, this is not actually interesting at all. I can write 1. I can write what? 2. None of them is true. Okay, so another question. What is the cardinality of this? And what is the cardinality of this? What is the cardinality of this?
How about there's a question?
Yes?
Uh,
Louder, please.
why is number 2 why is it false for the first one?
Okay, when you say A belongs to B, what is A? A is this one. Yes? If I ask you what are the elements of B and list them, the first thing you will tell me is 1. The second one you will tell me 2. So these are the elements of B. Yes? But as you see, none of them is this one. Because it has curly brackets around it. So the curly bracket 1 as a whole is an object. Yes, I want you to understand that. So if I ask you A, what is A? This circle, this is what is inside is A. What are the elements of B? Only 1 and 2. But none of them are exactly this. So this means that A does not belong to B. Okay, what is the cardinality of the empty set? What's the cardinality of this set? What's the cardinality of that set? 1. Okay, but I want you to understand, are these two the same? No, because they are. Okay, but what about this one? What's the cardinality of this? It's still 1. What is the element of this set? The element of this set is this one. So you take one curly bracket from here and there, and then what is left, they are elements. Yes, for example, that's the cardinality of this set is still 1. So, for example, I have this. So what's the cardinality here? What's the cardinality of this set that I just wrote? 3. But why you said 3? You say this is one element. This one is the second element. And this one, exactly what you see, this creature, is the third element. Yes? Okay, so now let me just try to ask you some questions. Do you remember, you should be able to write all possible subsets of a set. Yes? For example, let me just remind you about that. For example, a very simple example, A is 1 and 2. I want you to write all possible subsets of this set. First of all, I want to check your memory. Do you remember how many of them are there? Yes?
2 to the n, where n is the number of elements.
Elements. So here in this case, 2 to the 2, which is 4. And then you remember, if I ask you to write all possible subsets, how do you do that? You start, you don't need to respect the order, but it is better to be organized. So if you tell me this, I will start with the empty set, because the empty set is a subset of all sets. So I start my list with this one. And then I ask myself, what is coming next? So what is coming next? I would write 1, and I would write 2. Yes? So these are the only singletons. Singleton means a set with one single element. Okay, can I have another subset with exactly one element? No, this is done. But what is the last coming in your list? Is the set itself, yes? So how many subsets you see? 1, 2, 3, and 4. Okay, let me ask you to write this. All the subsets of this one. What should I write? Yes?
The empty set.
The empty set? Is that it? Yes, Aaron?
And the set itself.
And the set itself. Because I told you, what is the cardinality here? 1. According to the rule, it should be there should be 2 to the 1 subsets. So there should be 2. And of course it is clear, because I always start my list with the empty set, and I will always end up with the set itself. So the subsets of this set is this one and the set itself. Yes? These are the subsets. Okay, let me make it a little bit better. So what about this one? I want you to list all possible subsets of this set. First of all, tell me, what is the cardinality of the set I just wrote? 2. So how many do you expect? How many subsets do you expect? 2 to the 2, which is 4. The first in the list, even you don't need to look at the set. The first in the list is always the empty set, and the last in the list, you don't need to look at it. It is the set itself. Of course, you have to look at it, yes. This is the first in your list. This is the last in your list. Okay, but are these the only ones? Of course not. You expect 4 of them. So there are 2 more. This I want you to write, because the important thing here is the number of curly brackets you use to write them down. So I just want you to write it down and just tell it to me. I want you to write something similar to these here. But I told you that the only thing here that matters for me is the correct opening curly brackets, the number of curly brackets. I want you to follow the correct punctuation rules. Yes, Hussein?
Curly brackets, curly brackets, curly brackets.
Yes, curly brackets, empty, and then curly brackets, empty. These are the only ones. Yes? So these are the only subsets of this set. Okay, I want to make it a little bit more complicated. Okay, but I want, you have to be a little bit patient, because I want to increase the cardinality to 3. So how many do you expect then? 2 to the power of 3, which is 8. Of course, if I give you this, I'm sure that everyone can write this down. So for example, ABC. If I ask you to write all subsets of that, that is easy task. But let us just do it like this, okay? So I would say that, let me write the empty set, and this, and that. So this is a set with cardinality 3. This is one element. This is the second element, and this is the third element. So we want to write all possible subsets again. So again, the first one in my list is the empty set. The last one is also very simple, just copy and pasting. But of course you have to be careful here. So these are easy. But the intermediate steps, okay, we can list all singletons. Yes? The singletons means the sets containing exactly one element. So can you tell me what do you write first? Yeah, you just open curly brackets and then put this element here. This is one of them. This is a subset. This is a subset of this set. Of course, this is also an element of that set because of the second one. So that's a coincidence. Okay, but what about next? What should I write next?
Curly, curly.
Yes, curly brackets, the empty set. That's the second one. And what is the third one? So I open curly brackets. I take the third one and put it here. It's not hard, but you have to be careful about the number of curly brackets that you put there, yes? Yes? Okay, now, is there any more with one single element? No. So what is the cardinality of this 1? What is the cardinality here? 1. What's the cardinality here? 1. Yes? Okay, but now I want to have two element subsets. So I open a curly bracket, choose 2 of them, and put them here. So this becomes the empty set, and this one. Yes, is that clear? And then again, I put another curly brackets here and there, and then I choose this one and the last one. So be careful in writing them down, yes? Am I right? Yes, so you see, I took exactly this one and put it here, and I put this one in here. But I also have one more, yes? I can open curly brackets and now choose these two and put them here. So, and then 1, 2, 3, 4, 5, 6, 7, and 8. So as expected. It's nothing, I just want you to work with these things so that you can get used to it. Okay, any questions? Okay, I will stop here. We will continue later.